at some point in your Algebra 2 career in high school, you've probably heard of the concept called E. So this video is going to seek to answer the question of what is E, or for example, how can we come up with a way to approximate E out to however many terms that we want to. So let's find out where it comes from. So E is commonly used as the base of the natural logarithm. So ln base E, we usually omit that because base E is assumed if you're using a natural logarithm. So natural logarithm base E of y equals x, or in other words, E to the x equals y. So normally, we would just omit that E in there. So, okay, this has a lot of applications in algebra. So we're going to find out what this is exactly. So let's think back to our concept of exponentials, which is what this is, because we have a variable as an exponent, and there actually is a very nice application of exponentials in our compound interest that can be used to arrive at E. So we have C equals P times 1 plus R over N to the nx, for example. So this would be like if you have some compound amount equals your principal times 1, 1 being for 100% of the principal you begin with, plus your rate over your number of compoundings per unit of time x, okay, to the power of nx. So we care about the particular application of what happens when P equals 1, R equals 1, or rather we have a 100% return rate in 1 unit of time. So this is going to lead us to C equals 1 plus 1 over n to the n, and what happens when we try to maximize this? Well, let's just take n as it approaches positive infinity and see what happens. So it turns out that this is where E comes from actually. So let's say that E equals C maximum, or C max, which we're going to say is equal to the limit as n approaches infinity of 1 plus 1 over n to the n. So to the untrained eye, you might think, well, n is in the exponent position here, so does that not mean that this is going to be infinite? Well, it's not quite so easy because we have an increasingly diminishing part here that we're adding to the 1 that we're compounding each time. So actually the result that we get might not be what you would expect. And we're going to find that this is actually going to have E as an asymptote, where I'm going to come up with what's called a binomial expansion here, and we're just going to expand this out into something that ultimately we're going to be able to get increasingly more significant figures of E based on however far that we go out. Now, in theory, if you really could write out an infinite amount of terms, then yes, you could figure out what E equals exactly, because we would have a 1 over n to the n piece at the end, which is just going to go to 0. But because we can't actually write an infinite amount of terms, we just have to take the approximation as it comes. So binomial expansion, if you have never seen this before, anytime you have something in the form of a plus b to the n, you can write that in the form of a to the n plus n times a to the n minus 1 times b to the n minus 1. So the power of a basically is going to be continuing to decrease by 1 each time, and b is going to increase each time because the n's are going to cancel out here. So now the pattern continues like this, plus n times n minus 1 over 2 factorial, and multiply this by a to the n minus 2 times b to the n minus quantity n minus 2, and the pattern continues like this, n times n minus 1 times n minus 2. So really, if you think about it, this contributes to n minus 0 piece, but we don't need to write that, so it's just n over 3 factorial times a to the n minus 3 power times b to the n minus 3. And if you continue this pattern all the way down, you're going to find that you're going to get b to the n is going to be what you end with, because we're going to have a power right here where you're going to have n minus n, which is a to the 0th equals 1 times this other piece, so we don't need to actually write that. And for b, we would have b raised to the n minus the quantity n minus n, or n minus 0, and that's just b to the power of n. So okay, let's go ahead and clean this up a bit. So this is going to be equal to a to the n plus n times a to the n minus 1 times b, because remember, we have to cover all the possible different combinations of things that we could have here. And we're going to go ahead and write out the next coefficient, because that's what these are going to be here with the n's and the factorials in them. So n times n minus 1 over 2 factorial times a to the n minus 2, and that's just going to be a b squared piece, plus, now we're going to do this part, n times n minus 1. Now normally in factorial form we don't actually multiply this out yet. That's going to be important later on for us. So because we're going to have to bring something out and cancel it, as we'll see. So n times n minus 1 times n minus 2 over 3 factorial times a to the n minus 3 times b to the 3rd, plus all the way down to b to the n. And this is generally how a lot of textbooks will present this concept to you. So now the task that we have is we're going to take this 1 plus 1 over n to the n factorial piece, and we're going to expand this out, and then we're going to take n approaches an infinite amount, and basically what's going to happen is a bunch of the n pieces are going to end up canceling out, as you'll see. So okay, so we have e to e equals c max equals limit as n approaches infinity of 1 n plus 1 over n to the n. And we're going to say that this is going to equal, using our binomial expansion, we're going to say this equals limit as n approaches infinity of some large expansion that we're going to end up doing here. So this is going to be 1 to the power of n in this case, plus n times 1 to the n minus 1 times our b term, which is 1 over n, and we're going to take that to the first. I'm just writing a bunch of this out for the sake of completeness, even though, as you can see, 1 to the n, that's just going to end up being 1, and all these other things in here are going to be simplified. So what else do we have to do here? Well, now we can look at n times n minus 1 over 2 factorial times 1 to the n minus 2 times b, and then our b term in this case is 1 over n, and we're going to square that. And okay, so continuing on, we're going to have plus 1 to the n minus 3, but first we're going to have to write the coefficient. I'll write it this way for the sake of just trying to be as consistent as possible. You can see this, so n times n minus 1 times n minus 2 over 3 factorial times 1 to the n minus 3 times 1 over n to the third plus dot dot dot. This is going to go all the way down to 1 over n to the n. Okay, so now our task is we're going to try and clean this up a bit. So as I said, the 1s to the power of anything here, that's just going to be 1. And unless we're adding the 1 like we're doing initially, then 1 times whatever it is, that's just going to be able to cancel out. So this goes away, like we can take away the exponent on that. We can take away all of the 1 to the whatever powers, so just cancel those out, get rid of those, and notice how here we have an n times the 1 divided by n, so we're going to cancel the n's out there. And is there anything else that we can do? Not really yet. So moving on, we're going to have this equals the limit as n approaches infinity of 1 plus 1 plus some, let's multiply this out now, equals n squared minus n over 2 factorial times some 1, let's go ahead and square that, so 1 squared is 1 over n squared. Okay, what else can we do? Well, let's multiply this out over here, so we already know that n times n minus 1 is n squared minus n, so really what we would need to know is what is n squared minus n times n minus 2. Well, okay, let's go ahead and multiply this out. So this is going to equal n cubed times minus 2n squared, and we're going to have a minus n squared piece in there, so we're going to combine like terms plus 2n, and we're going to have that multiplying this piece out gets us to n cubed minus 3n squared plus 2n for that little piece in there. Okay, so let's go ahead and put that in there. Equals n cubed minus our 3n squared plus 2n over 3 factorial. And remember, we have this 1 over n cubed piece in here. So, and we also have the 1 over n to the n factorial continuing all the way down the series here. So now the trick that we're going to do is we're going to take an n squared or an n cubed out of all these pieces, because we want to get rid of the 1 over n squared and the 1 over n cubed here. So let's go ahead and do that. So this is going to give us a limit as n approaches infinity of 1 plus 1 plus n squared. Taking this out, we're left with 1 minus 1 over n divided by 2 factorial times 1 over n squared. Notice we have an n squared on top, n squared down here, so we can get rid of these. Plus, let's take the n cubed out now over here. So that's going to give us a 1 minus 3 over n, looks like. And then we have a plus 2 over n squared. And put that over n factorial times 1 over n cubed. And let's go ahead and get rid of the n cubes there, plus dot 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 1 over n to the power of n. And okay, notice how here there's no way to factor this further, so 1 minus 1 over n is what we have, and we are able to factor this one though, as you'll see. So let's go ahead and do that. So equals limit as n approaches infinity of 1 plus 1 plus the quantity 1 minus 1 over n over 2 factorial, and go ahead and add this other piece that we're going to put in here, and we're going to make it be 1 minus 1 over n times 1 minus 2 over n, because if you multiply this out, then you're going to find that it equals the 1 minus 3 over n plus 2n squared piece that we have up here. Okay, so now put that over 3 factorial plus dot 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 1 over n to the power of n. Now we can't simplify this any further, so now we are actually going to see what happens when we take n as it approaches an arbitrarily large amount. So let's go ahead and put this in. So now this is going to equal the quantity 1 plus 1 plus 1 minus 1 over n, but notice that 1 over an infinite amount approaches 0, because you're taking 1 over such a large amount that it's practically going to be 0, or as one of my teachers used to call it, you have practically nothing. So this goes to 0 over 2 factorial plus 1 minus n. It's 1 minus 1 over n. And remember that goes to 0 as well. times 1 minus 2 over n, that goes to 0 as well. There's 2 over n, 1 over n, 3 over n. It's still going to be some constant over an infinite amount, which we say the limit of that is 0. So divide that by 3 factorial plus dot 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 1 over n to the n, and that's going to be basically like saying 1 over an infinite amount to the infinite power. So that's going to be like basically saying 0 to infinity, or basically that whole part 0. So now after we do this, what are we going to be left with? We're going to have that E can be represented by 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus dot dot dot. And if we could extend this out far enough, then you would see that the last term would technically be 0, but well, it would be as close to 0 as you could come anyway. So yeah, so this would be how we would describe E from a binomial expansion. And if you do this out to enough terms, you'll find that it gets increasingly close to a value of roughly 2.718. So normally this is about as far as you need to go for like an Algebra 2 course. Going out anything past like the thousands place, you really don't need to go that far. So I mean, for pretty much everyone's purposes, E approximately equals 2.718. So okay, this is how you come up with that, and hopefully you found this helpful, and I'll see you in the next one where Joe shows you how.